Uh, Good morning, everyone, and thanks to the Geological Survey of Queensland that they invited us and that we can present some of the work that we did together with them last year. And in this project, we tried to have a look at some new ways how we can use pre-competitive data in exploration and mapping. So not only for the industry, but also for the Geological Survey. I'm actually from the Mineral Resources, not from Data 61, but I've worked with a number of people in Data 61 that helped to make this project happen. I'm just going to quickly go through some of the machine learning techniques that are used, and you've heard before that this is the way probably to go, and it is. These techniques have been used in geosciences before. I will focus on basically two problems, and that is using point observations, either geological or geochemical, and some covariate data like geophysics, like the interpreted maps or geological models, that then can be used to create some features that help us help the model that we train to get some estimation of either a location for targeting, so location of a mineralized location, or a prediction of a geochemical value, or a prediction of a geological unit. And that will then help you, of course, in targeting. I will quickly go through the process that is involved in all of this. So first of all, we need to clean the data, and you've heard before that that's probably the bulk of the work that we need to do. Deal with missing data, deal with detection limit and consistent units, and all that metadata that we can source out of these databases also helps us to make some informed decisions that will help us run a better model. What we do afterwards is what we call feature extraction. So that is generating some additional layers based on the raw data or the covariate data. You can imagine creating a derivatives out of the geophysics, so first vertical derivative, or mapping automatically the structures that can be detected by algorithms in the data, and then creating distances to these structures. We can also use other transforms like wavelets to characterize the different patterns. And last but not least, we can perform some data reduction so that the algorithm runs better. This is, however, not that necessary due to the recent developments where the computing power is so good and the algorithm so robust that we can deal with thousands of layers potentially. The next step is to select the right model. So that depends on what we want to do. Do we want to classify a lithologic unit, or do we need a regression type method where we basically grid geochemical data? Or do we actually have training data to do the process, or do we need to cluster our data based on the internal covariance in the data? Now, more and more, these algorithms are used as probabilistic, so they not only give us a prediction, but also an uncertainty measure on the prediction, which then helps us, of course, say, are we somehow true or not? What we need to do with each of these models is to validate it, so that we don't only learn the data that we used for training, but also can generalize over data that the model has not seen. And we tend to do this with cross-validation. That means withholding a little bit of the training data set to then confirm whether the model performs well. We also use other performance measures like mean square error or the coefficient of determination, or something called precision or recall, which just measure how well the model works, how well can we map the true positives, or how much false positives do we generate in the model. After we do this, we can then predict for the data that the model has not seen. But we have to be aware during the prediction that usually in geological applications our training data is biased towards areas where we have sampled, right? And there can be a phenomenon that is called covariate shift. So that means, and it comes back to non-stationarity in geostatistics. That means that the distribution of our training data is fundamentally different from the distribution of the data that we try to predict on. And it's good to know that this exists and we can estimate that. After that, we, of course, have to communicate the model results, visualize it, and interpret it, whether towards geology or towards the data side of things. Now, I'm gonna, in the following slides, I will focus on 4 selected components of the collaborative projects that we did with GSQ in last year. And this will be by no means exhaustive. The report will come out soon, so I hope you can then go to the report directly. But I will touch on mineral occurrence mapping, on automated geological classification, interpreted geology anomaly detection. So from an existing map, look at how anomalous are the units in the geological map, and then on modeling the geochemistry and using that as a proxy to traditional mineral prospectivity mapping. Now the area, again, we are in the Northwest Mineral Province, and we're going to be focusing on that area, unfortunately, but for some of you it will be interesting, hopefully for most of you. We know that that's an area of endowment where we have produced some spectacular finds in the past, and it's an area where we have very good coverage of pre-competitive data, but also very good geological maps, and so that's why we selected it as a good starting and testing point for this project. Now in the mineral occurrence mapping, we actually looked at something that the GSQ has already done, and they actually did a 3D estimation of the mineral prospectivity in that area using weights of evidence. It's basically based on comparing the location of known mineralization with the underlying covariate data and trying to predict where similar locations in the area exist. Now we try to compare it with a machine learning method called logistic regression, and had a look at how these two methods actually differ. Now this is the outcome of the weights of evidence, just to reproduce from the study of GSQ. And you can see that it has slices for different depths, and we used inversion of the geophysics from gravity and MAC to estimate the susceptibility and density for each voxel in the model. And we also use structural features, so the proximity to them and so on. And you can see that we can predict the deposits quite well. Maybe we overrely too heavily on the structural components, but as you know, the deposits are structurally controlled. If we compare it to the logistic regression, here in this example, we can see a little bit more detail, less dependence on the structural features. But generally, again, we can capture the deposits quite well. We need to be, however, mindful of the limitations, and that's the fact that we only use 15 training samples to actually produce this model. We can also estimate the goodness of fit. So for the logistic regression, this is a log loss measure, so the lower the number, the better. We get a little bit better prediction for the logistic regression than the weights of evidence. And we can also have a look at the receiver operation characteristic curves for both of these. And again, the machine learning or the logistic regression performed slightly better and delivers less false positives than the weights of evidence. Now I will move into machine learning and how can we use it to find granite outcrops in the area. So we used the field observations that are stored in the database of GSQ. We had 6,000 surface observations to find basically six classes, so 5 types of granites and 1 class for non-granites. And we used, again, for this exercise, we used surface data, so digital elevation models, but also geophysical covariates and data from ester and so on. And we used a random forest classifier to do this exercise. Again, if we look at the results, on the left side there's the interpreted geology, and I forgot to say, we try to use the training data only in the outcropping areas where we know that there is granite outcrops, of course. And then we have to the right the model prediction and the difference between the model prediction and the interpreted geology, and also we can deliver the model probability. So in the difference, the red areas are the disagreements, the model probability, the yellow says high probability of that class occurring, the blues are low probability of the class occurring. And we can see that we can fairly well map the Williams granites, but we have quite a bit of trouble with the Calcadoon and the Marmonji granites. And that might be in part due to the geophysical response of these, but also in a larger part, when we actually look at the statistics behind this, in a larger part due to the training points that we had available for these for this exercise. So we can see that if we have low number of training points, we have trouble with classifying the particular granite type. So the Williams supersuite, we get higher precision recalls than the F1 score because we have basically 11% of the training samples actually cover that type of granite, whereas the other 3 we don't have that many samples. The application of this is, of course, for GSQ to go in the field and test some areas where where these outcrops were found or not. We also then said, let's try and predict outside of the outcropping areas, which is this example, and you can see again some indications of outcrops outside of the outcropping regions, and again a model probability which is highest along the outcrops, of course. You can see that there is a granite predicted in the far east, but that has also a low probability, so we can probably discard that. In greater detail, we can then sort of have a look, for example, here at the Williams suite or the Williams type granites, and see how the model performs, and see that we can probably predict granites underneath the quaternary sediments, but also there's a possibility that one of those bodies to the east might not be as extensive. Now the other thing that we tried was anomaly detection. So that means can we actually audit the existing map that we have from GSQ and say which units are anomalous, so which units maybe should deserve another look at. And we can use an algorithm such as the one-class SVM to calculate per class sort of per class anomaly and the distance to, or the perceived rate of anomalism for the class. Now the model that we used actually requires one parameter that we can vary, and that's the amount of anomalous data that we expect, and that's a parameter called nu. So this is a result based on the assumption that 50% of the data can be anomalous, and so the anomalies are in purple in that map, and the distance, so the degree of anomalism within these areas is displayed next to it, with the darker colors being more anomalous. And then there is, we can also compute a mean anomalous distance per unit. So that will tell us which units are the most anomalous on average. Now this is probably an overestimation of how much anomalous areas there is, but we ran a couple of these, and there is a 5% anomalous result here, and this one highlights probably the most important area. So that means the areas along boundaries of geological units where we can expect the most variance and discrepancies with the geology. But again, it provides some sort of measure of where we can go and sample or verify the map. The last example that I'm going to show you is basically trying to go away a little bit from the traditional prospectivity that we do, and try to use real data or more data, basically, because we can use, for example, the soil geochemistry and try to predict or create a regression of these concentrations over a larger area. So what we used it was the geochemical database of GSQ, and again training data from outcropping areas of in situ soil to inform the classifier, and then we used data from geophysics, mainly methods or only methods that would penetrate the cover because we wanted to actually test it, how well can we then penetrate undercover, or how well can we predict undercover. So we use gravity and magnetics and derive data sets from that. We use texture, so gray level co-occurrence texture measures, and also the distance to automatically detected lineaments. And you can see that we actually wanted to predict only for the Combi map sheet, but we quickly realized that we have not enough training data to produce some useful results, and expanded the training data all the way in the Eastern succession to have actually good estimate. We also try to estimate the covariate shift, so that's what I tried to explain previously. Does our training data actually match the prediction area quite well? And this is just an explanation of the covariate shift. So when the distributions of the training and prediction or query data vary too much, then the model, of course, is not as valuable. Now, this is the results in terms of statistics, and we use the coefficient of determination here. You can see that, of course, for gold, we didn't achieve quite good results. That was one based on the fact that the training points were scarce, so there was a lot of missing data. And secondly, gold, due to its nuggety behavior, is probably not a good element to predict on. But for the other three elements that we tried, copper, lead, and zinc, we got pretty good results. And the results were actually improved when we incorporated wavelet features in the model. We also then tried to estimate the covariate shift classifier accuracy, and we can see that we couldn't really discern the predicted from the training for the example where we didn't have wavelets, but we could very well discern those two in the case where we had wavelets. Quickly go through the results. So this is the model prediction for copper based on gravity and magnetics. We can predict on a large area, and we can see that we captured quite well, again, some of the deposits, and we also generate some targets outside. And again, we can provide model uncertainty. Here, the higher uncertainty means the less probable the result. But this is an example of where we actually try to use the wavelets. So the accuracy of the prediction is better, but we have to be aware that for a large part of the area, which is now masked, the area where we try to predict is vastly different from the training data. So to use the model in that area is not probably appropriate. This is a result for the lead. And now I know I'm over time almost, so I'll just go to the conclusions. So if we were to summarize what the project outcomes were, we hope that GSQ can implement some of those methods in their mapping to help augment the current mapping process, as well as provide some alternative products to perspectivity, to the traditional perspectivity, through enhanced gridding of the geochemical data. Now we know that these models are of course predictive, and they're wrong. probably, in some areas. So we need to validate those data-driven models on data that were acquired or that were not seen. And that comes back to collecting new data sets. So we hope that the uncertainty maps and the probability maps also help GSQ target areas where there is potential to update the map or update the result of the model. We know that there is a sampling bias. That's always going to be there. That's just the nature of the geoscientific data. But we have to be aware of it, and we have to try to estimate what the sampling bias actually, what is the effect of the sampling bias of the predictions that we create. And with that, I'll thank you for your attention, and I'm ready for questions. Thanks a lot.